So, hello everyone. I'm glad to have been given the opportunity to talk to you. This talk has the title, A Knowledge Graph Approach to Cross-Domain Data Integration, Implications for Planning. My name is Professor Markus Kraft from the University of Cambridge, also situated in Singapore with CMCL and the Computation Modeling Group in Cambridge. So, at the moment, we are in the phase of Industry 4.0. And that is characterized by the Internet of Things, cyber-physical systems, and Internet of Services. What does that mean? So we are in the process to go from digitization to digitalization. So the Internet of Things is interconnecting numerous devices and ubiquitous computing. This is the physical realm where this takes place. The cyber-physical system has a higher level of integration between physical and computational elements. They're deeply intertwined between physical and software components. And the Internet of Services shows here the cyber realm that acts on the devices. Okay, so we're using here cloud computing, heterogeneous environment. However, there are problems. And one of the problems is low interoperability. So there is friction of communication between these heterogeneous devices and cross-domain application. So there is ambiguity and lack of content. Now, what we propose here, that knowledge graphs may be the solution of this. Now, you may be familiar with the Gartner hype cycle. This is about emerging technologies, and you see these technologies go over time through different phases. And in 2019, you could find knowledge graph in the first phase, okay? And in 2020, ontologies and graphs have already moved forward and are heading towards the plateau of productivity, which basically indicates that this is a very hot technology. Now, what is a knowledge graph? I think most of you will be familiar with the Google Knowledge Graph, which helps to produce these nice boxes to the right. That happened first time in 2012. And here you see Barack Obama. And behind the scenes, the knowledge graph looks a bit like that. For example, Barack Obama is married to Michelle Obama. Okay, this is the data is basically represented in triple subject, predicate, object, and uses concepts that in their own right are also represented as triple. So it's a fully consistent representation. So we have basically used this technology to build the world avatar, which is basically a dynamic knowledge graph that represents the world. Okay, so the world avatar represents every aspect of the real world in a digital world in a world model. And it's a form of a general purpose, all-encompassing data storage and modeling framework. And it contains concepts and data describe the real world that are operated on by computational agents. So the agents and the data and the concepts are all in one. So, and this is a bit what it looks like, okay? So the dynamic knowledge graph is distributed directed graph, is based on ontological representation of data, which is here. It uses the concept of linked data. It contains an ecosystem of agents here in terms of instantiation and here in terms of running software. It is basically unambiguous. It is connected, scalable, it's distributed, accessible, multi-domain operable, and evolving in time. So it's not only in the cloud, it's also on the edge. And some people may have heard this name fog instead of cloud. It's fog. It's basically everywhere you want it to be. Now, this was just a very short idea of what the world avatar does. And We have several use cases, and just to give you an idea how versatile this concept is, I'll just show you 3 use cases, and then I will make a link to policy making. So what you see here, this is the buildings of Berlin-Charlottenburg. These are 22,000 buildings, and these buildings are in form of level of detail 2, and they are now part of the knowledge graph. So you can now zoom in, and you can now see what LOD2 looks like. And the idea here is, of course, to equip these buildings with more functionality. And we have started to do that in an example in Singapore. So what you see here is an HDB building block here at the higher level of details, LOD4. And you see we have highlighted the flat where we actually are going to instantiate also the pieces of furniture and the electrical appliances in this apartment. First agents that we've been developing in the world avatar contain an agent that is able to extract object pairs that meet specific distance constraints and unit type. So, for example, you could ask, find all shops in a 1 kilometer radius, and agent 2 retrieve each city object's average, minimum, and maximum distance to other city objects. So on the left, you see a snapshot of place graph, which basically shows, you can't read it here, but a Sparkle query that allows us to search the knowledge graph. Right. The next case is also directed towards cities. It's called combined heat and electricity. Here, we're looking at district heating, and district heating can play a key role in the energy transition. So you see on this graph, okay, CO2 emissions and primary resource factors. Okay, the primary resource factor is the ratio between the non-regenerative fuel input and the final energy use. In other words, the closer you're here to the left, the more environmentally friendly is the technology. And these are the district heating systems of Gothenburg, Vienna, Helsinki, Torino, and these are specific heat pump, oil, gas, and coal technical devices that are used in particular buildings. This just gives you an idea that heat pumps may not be such a stupid idea. Okay, so district heating is expected to play an essential role in cost-effective decarbonization. Key efficiency drivers is industrial waste, economy of scale, and electricity cogeneration. So you may get some extra heat from industrial work, municipal waste generation. Of course, it can reach a lot of households with that. And when you create heat, you can also create electricity, and that certainly makes it cheaper because you can sell the electricity. Right, so one thing is also clear, because of the need of decarbonization, we expect that there is an increasing integration of intermittent renewable energy sources, and that makes it ever more important to integrate smart energy systems, for example, sector coupling and prosumer trading. So in the past, we've been working together with Stadtwerke Pirmasens, which is actually where I'm sitting right now, and they have a district heating system. You see there's a municipal waste plant, there's an energy a municipal utility plant. It has boilers, different boilers. It has a gas turbine, combined heat and power gas turbine. It can co-generate electricity all these boilers, including gas turbine, can create heat. They can also fill a storage tank, and there is additional energy from waste, from a waste plant that also goes into district heating, and of course there are the consumers. So there are multiple degrees of freedom to satisfy customer demand: boilers, gas turbine, and the municipal waste plant. Right. So far in the stratigraphic thermosens, they've been using an Excel-based optimization. So they have an evaluation of most beneficial high-level operation, set point several times a day. Discontinuous evaluation of potentially profitable gas turbine operations. And the overall strategy was largely driven by heuristics and personal experience. And it was all in a static Excel model. And this is just a snapshot of any Excel. I'm sure everybody has seen this before. So we have now implemented this in our knowledge graph. And what you see here, we have added heat load forecasting. And you can see here the predicted in the past heat load demand. And here you see the error. So this is within, most of it is within 1.5%. So this is a very good forecasting system. And as a consequence, we will be able to use this forecasting to do optimized heat generation. And you can see here how the boilers in the gas turbine have been used overall during the year. And the key figure is that, and the gray one was the historical data. The red one is what has been achieved with our control software, with the control agent within the world avatar. And we were able to generate cost saving of about 20% and more, which is a very positive result. So finally, I would like to talk about the fuel poverty and heat pumps. So fuel poverty is an indicator that is defined as follows. So when a family has spent the required amount of money to heat their home, what have they left with what is left of the residual income below the official poverty line? So there are three important elements in determining where a household is fuel poor. So it's household income, household energy requirement, and fuel price. Okay. So what you now see is data from the knowledge graph. So we are zooming in the greater Manchester region here, and the northeast, London, and if it's blue, then there is a low amount of fuel poverty, and if it's red, there is a lot of fuel poverty. So you basically see the poorer regions in the country. Okay. So what you see here is a coefficient of performance of an air source heat pump in northeast Derbyshire, okay, that's here, and Westminster in London. So what you can see, this is the coefficient of performance, okay, in these two regions. And you can see that this is a monthly legend on the x-axis. You can see that when it gets hot, the efficiencies go up. When it's lower, the efficiency is low. When the temperature is lower, the efficiency is lower. And the gray shaded area shows the coefficient of performance with the minimum and maximum temperature that's recorded over the year for these two regions. So the minimum and maximum coefficient of performance and the corresponding air temperature throughout Great Britain in March 2019 are basically shown in these two vertical bars. It is clear that they are highly correlated. So in other words, the colder it gets, the less effective the heat pumps are. Okay. So now we move forward and now we look at the synthesis. So what you see here are regions of high fuel poverty that would experience large increase in the fuel cost. So again, we can zoom into London, we can zoom into the Northeast and into the Southwest. So I summarize regions where new electrical bills cost more than current gas bills are all colored red. Okay, so this is where fuel poverty is made worse and regional, and that enables us to have a regional aware policy making. So clearly, people in the north that are suffering of fuel poverty, they will have even worse situation as before, and people in the south, they are, because they're in warmer regions, they don't suffer the introduction of heat pumps and can actually benefit much more than the people from the north. And with that, I've basically connected our knowledge graph to policy making, and of course it's just a start, and there's many more studies to come. So thank you very much for listening, and I hope you enjoyed this talk.